Okay, let's get to the main content. First of all, it's an introduction to regression, and we will start with the definition of regression. I think I'd better just do a slideshow from here. Okay, so I cited the definition from the textbook, where it says regression analysis is a method for investigating the functional relationship among variables. So here it's functional relationship among variables. On Wikipedia, it says in statistical modeling, regression analysis is a set of statistical process for estimating the relationships among variables. So there are some similarity between these two definitions. Let's look at what Harvard Business Review says. Regression analysis is a way of mathematically sorting out which of those variables does indeed have impact. It answers the questions, which factor matters the most, which can we ignore, how do those factors interact with each other, and perhaps most importantly, how certain are we about all these factors. I think this is a very, very thorough and detailed definition. And I also cited this definition here. It's a functional relationship between two or more correlated variables that's often empirically determined from data. And it's used especially to predict the values of one variable than given values of others. So this one mentions the prediction part. Well, I have this 4 definition here just for your reference. Whichever one you like the most, you can use it as your definition to the regression analysis. But among all these 4 definitions, we see it mentions the relationship among variables, and there are some other things that some other conclusions we can draw with our regression analysis. We will start with a simple linear regression, and this is the simplest regression model. So we'll take a look at first. So the first case we consider is modeling the relationship between 2 variables. So only 2 variables, y and x, in a straight line. That is to say, we model y as a linear function of x. So both y and x are random variables, and we're going to model them in a linear relationship. And then we collect data in pairs. So we denote those like a pair of x1, y1, and x2, y2, etc. to xn, yn. And x1 is the first value of the x variable, and y1 is the first variable of y variable. And here I use this capital Y and X to denote vectors. And this small x and y are just a single value in this vectors. Okay, and some more definition here. X is called the explanatory or predictor variable, and y is called the response or dependent variable. Whichever pair of definition term you want to use, people will know what you mean. Well, what does that mean in practice? Like explanatory variable, response variable. So X is thought of as a possible predictor for Y. So that's another reason why it's also called predictor. And in experiments and in observation study, it has sort of different settings. So in experiments, X is set by the experimenter and Y is observed. In an observational study, both X and Y are observed, but it's thought that the outcome y would depend on the outcome x. So if x is, so this is just a small example. X is the number of hours you train, you practice, and y is how long you take in the race. Well, the common sense is likely that the value of y would depend on the value of x here. Well, for this simple linear regression models, we always draw a scatter plot first just to get an idea of the strengths, the form, and the direction of the relationship between two variables. And on the next slide, you will see a very clear pattern between x and y. And here, the variables we are considering is the percentage of voters for each state who voted for President Obama in 2008 and 2012. Let's look at this plot. So on the x-axis is our explanatory variable x. So that's the percentage of voters who voted Obama in 2008. And on the y-axis is our response variable, which is the percentage of voters voted for Obama in 2012. It's very clear that it's a linear relationship between x and y, so that it's suitable to do a simple linear regression in this case. Yeah, I just want to emphasize that a scatter plot is very important, that for you to investigate what kind of relationship between these two variables and choose the proper model for the regression. Well, in the previous example, the first few entries in the election data set would be like this. Well, it's hard to read the number from the plot, but I just put it here to give you an idea how did we define x1, y1, x2, y2. So for example, here for the first data point, we can probably see it's well, sorry, I mean in the data set it would be like this, but it's not necessarily from here or from whichever. It's just hard to find the right point from here. But this is what our data set would be look like. And you use this data set and do a plot like this, and then you can get the regression going. Well, I also put the meaning of this data pairs for the first data point. Data pairs, it means 37.7% of Alaska voters voted for Obama in 2008, while 40.8% did so in 2012, and so on. This would be for another state, and then this is for another state. But this one is corresponding to Alaska. Okay, let's get into a little bit more of the theory. We want to model the relationship between x and y, so that if you are given a value for x, say x equal to small x here, so it's some value that you know, then you can predict the value of y. Restating that, we want the expectation for y given a value for x, and we write it like this: the expectation of y condition on given the value of x being this small x. To force the relationship to be linear, we set this expectation equal to the equation of a line. So this is a linear it's a linear relationship, and it's just first order. That means it would be a line, a straight line. Okay, and this beta 0 and beta 1 is the coefficients that we are going to estimate from the data we have. Yeah, and beta 0 is called the intercept, and beta 1 is the slope of that line, of that straight line. Well, we have the random variable y observed at n independent realizations, y1, y2, until yn. And the random variable x, we also have x1, x2, up to xn. So this is just reiterate the definition of data pairs and the order of our data set. For example, for the fourth participant in a race, x4 is their time training and y4 is their finishing time. And in the previous example, we have our x1 being the water percentage in Alaska, and y1 is in Alaska for 2008, and y1 is the percentage voted in Alaska in 2012. Yeah, this is just another example, but we are like formally defined as y from y1 to yn and x from x1 to xn. And for a linear relationship of y on x, we have this yi equals beta 0 plus beta 1 times x. Oh, I think there should be a xi here. Sorry for this typo. I'll correct that before I post the slides online. And the value E here, if you notice, is known as the random error term of this yi. This is important because it allows for some random chance that y would not be predicted precisely with with our linear relationship. So that's the wiggle room around this straight line. And it's highly likely that for every participant in the race, y will be exactly equal. Yeah, it's highly unlikely that y will be exactly equal to this beta 0 plus beta 1 times x. So this random error accounts for the unexplained variation in this relationship. For now, we assume that the variance of y once x is given is sigma squared. So that will be the variance of the error as well.